morning, everybody.
Hello.
Good morning, all.
Good morning, ma'am.
Only 80 members have been joined. That is only 78. 78 are joined now. Let us wait for a minute. We'll see whether some more are going to join the class. I hope everybody has joined the Edmodo. Anybody remind? Everybody joined the Edmodo or not?
Yes, ma'am. Yes, ma'am.
Hey, Sam.
Okay.
Yes, ma'am.
Okay, okay.
Go.
I will track out all the numbers today, whether everybody had joined the rooms or not. And whoever joined, please complete the quiz by evening. It closes by 9 p.m. today. Right? So after 9, it will not be open, it will be get locked. Right? So let us. Hello? See, somebody are getting noise at their background. Please unmute yourself. Of course, I'm going to mute you all once the class starts now. Right? So let us start our session. Yesterday we gone through the details of the modulation, right? How the modulation goes on. What do you mean by the modulation? What is the need of the modulation? And all those things, right? And we have seen the example of amplitude modulation. And now today we also see how the other modulation will happen. See, as we, in the last class, we discussed about the signal equation, how the particular signal is going to be represented. We have seen an equation which is going to be represented a sinusoidal wave. How a sinusoidal signal will be represented with 3 parameters mainly. That is the wavelength, the phase, the amplitude, frequency, and the phase angle of the signal. Those 3 will be considered as the main features of a signal. Using these 3 characters and based on these 3 characters itself, we will be posing on to the modulation procedures, or we are following with the modulation procedures. And we also discussed what is the need of the modulation. As the signal which has been radiated into the air will be passing through different areas, and reaching different heights before reaching the destination, started from the source. So started from the source, it is going to be reaching the destination while passing through different areas and moving over different geographical areas and landing over different heights of areas, and it is going to reaching the destination after going through all these things. And while doing this, that is landing on different areas and landing its energy on different heights of geographical areas, it is going to losing its own energy. So before reaching the destination, it is going to losing that particular energy levels. So if it is going to be continuously losing its energy levels while passing through all these sources and all these areas, whenever it is going to reaching the destination, it will not be available to the receiver with its whole strength with which it has been sent by the source. So what the receiver has to do, if he doesn't receive the corresponding signal with the original strength. So to overcome that particular loss of energy or loss of the originality of the signal, we've been gone for the modulation. So how that particular modulation happens through, how the modulation of the signals will be done through has been explained, and it has been identified that a signal which has been radiated in the air, will be, a signal has been radiated in the air, will be possessing three properties mainly, and it will be affected through those three properties itself. Based on those three properties or the characteristics, the modulation of the signal will be done. That is nothing but the message signal modulation will be done. So what are those three characteristics? Before getting into that particular three characteristics, we have been saw that how a signal will be represented mathematically in an equation, right? How a signal will be represented mathematically in an equation, right? So this is the equation that we saw yesterday. S of t is equal to S naught into sine of 2 pi into c by lambda into t plus pi t naught. So here S naught represents the maximum amplitude of the signal, or the data that is being, the voltage level that is going to be represented in a signal while it is radiating through. There is a maximum peak of data that is being carrying over by the signal. And as you are going to representing the sinusoidal signal, it is being converted into the sine form, trigonometric sine form, taking into the 180 degrees variation. We also included the c by lambda. C is the velocity of the signal with which the signal is being transmitting, and lambda is nothing but the wavelength of the signal, whereas wavelength is the total lapse of a signal in a single cycle of its transmission, and t is the time interval at a particular time unit, and phi is the phase angle of the signal where the signal is going to be changing its direction while transmitting. Okay, no problem. Number 57. You are going to be tracking for the remaining session, right? And coming to the F, it is of the, and in the next step, C by lambda is been replaced by the frequency. That is nothing but frequency has been defined with the total velocity of the signal by the wavelength of the signal. So that's why it has been replaced with C by lambda with F in the next step. So here the signal has been represented here. That is, the main parameters in the signal are the amplitude, frequency, and the phase angle. Based on these three parameters itself, we are going to implementing the modulation. So modulation is nothing but you are going to rendering, or you are going to changing a signal called as a carrier signal, which is a separate analog signal, which is going to be modulated and changed according to the properties of the modulating signal or a message signal, through which you are sending the data to the particular destination, through which you are sending the data to the destination, right? So here a technique by which you are going to altering the frequency of a carrier. Here the carrier signal is represented with as a suffix C, a set of carrier frequencies used for wireless transmission, in which you are going to change either the peak amplitude of the signal SC, or frequency of the signal FC, or phase angle of a signal pi C. Okay, whereas the modulating signal parameters are going to be represented as SM, FM, or pi M. Here the carrier signal parameters are being given, right? So depending upon the parameter that we have chosen, the modulation techniques will be defined. Already we discussed about the list, that is the amplitude modulation, frequency modulation, or the phase modulation, right? See, already we saw how the modulation has been implemented. I illustrated you for that. Okay, how the modulation will be implemented, how the carrier signal will be chosen, how the particular modulating signal will be chosen, how they both are going to be superimposed, and one of the parameter will be get highlighted. Right, now we will see how these three will be happen to, and how they will be implemented technically. We will see internally. Right, we will see some images now illustrating the amplitude modulation, frequency modulation, and also the phase modulation. Then we will see technically how they will be implemented internally, taking the parameters into consideration, right? See, here it is the Are you able to see the screen?
Yes, ma'am.
Yes, ma'am.
Okay, okay. Now I'm showing you the amplitude modulated signal, right? See, on the same time plot, on the same graph, here the information signal is being taken like this. That is, the signal is going to be carrying the information in this manner. And the carrier signal has been chosen with the uniform frequency and uniform amplitude, whereas our information signal is been varying its frequency and also the corresponding amplitude. The x-axis has been taken on the amplitude side, and whereas the the x-axis has been taken on the time, and the y-axis is implicating the amplitude, right? Here the amplitude has been varying for the modulating signal, that is nothing but the information signal or the message signal through which you are sending the information, and the carrier signal in which you are going to changing its properties, whereas its frequency and the modulation are being uniformly taken. Its amplitude or also the frequency has been taken uniformly. How this particular amplitude or the frequency of our information signal is going to be superimposed on the corresponding carrier. See, I have shown you yesterday in a different way. That is, you are being superimposing the carrier with the modulating signal whenever the corresponding carrier is of lower value when compared to the modulating signal. When the carrier is having the lower values when compared to the modulating signal. Here, the carrier has been taken with a normal frequency, that is uniform frequency, and also the uniform amplitude level, right? And here this carrier is going to be changed according to the modulating signal. It's changed according to the modulating signal. Our carrier is like this. Internally the carrier is like this. Internally the carrier is like this, and this carrier is going to be modulated by superimposing our modulating signal. See, this is the here, the internal signal that we have seen here, whatever the frequency carrier signal is the carrier signal, which is being changed according to the information signal values, whether the frequency or the modulation, whatever it is, amplitude level. According to the level of the amplitude of the information signal and also the frequency of the information signal, the carrier has been superimposed here. The dotted line that you are going to see here, is the modulating signal or the information signal. It is being superimposed over our carrier. It is being superimposed over our carrier signal. This carrier signal is conveying the signal of our information over it. The carrier signal changed according to the properties of our modulating signal, and it is being conveying in that way to the destination. So at the destination side, we are again implementing the demodulation procedure. Why? Because these two signals are being sent as a single signal here. These two signals has been sent as a single signal here, and they have been sent as a single AM signal, that is amplitude modulation signal or amplitude modulated signal. This signal has been received by the corresponding receiver, and the receiver is going to be demodulating the signal now. So whenever the receiver is going to be demodulating at his side, then he is going to be dumping this particular outlier of the signal. this particular outlier of the signal separately by this carrier. Carrier is going to be separated, only remind with this particular outlier. Whenever he has been remind with this particular outlier, then he is going to getting this information signal outlier or information signal structure of the information signal. Obviously, he is going to getting the original signal. Because of this superimposition, of our modulating signal over the carrier, even though our signal while transmitting through the different geographical areas and geographical heights, it is not going to losing its energy. It's not going to losing its information at any cost, as carrier is going to be guiding us or guiding the modulating signal. As carrier is going to guiding the modulating signal, our signal will not lose any parameters while reaching to the destination. So this is about the amplitude modulation. I think I am clear with this picture, whatever we discussed in the last class or the yesterday class. Isn't it how the amplitude is going to be varying? Is it clear for you? Is it clear for you?
Yes, ma'am.
Right.
Yes, ma'am.
Right. Now I'll move to the another modulation.
Yeah.
One second. See, are you able to see the signal now?
Yes, ma'am.
Right. This is the FM signal modulation. See, the information signal is like this. The information signal is like this. And the carrier has been chosen in the similar way. That is nothing but having the equal amplitude and also equal frequency. Now, the FM signal, that is the frequency modulated signal. What you are going to be changing here, the carrier signals frequency has been changed. The carrier signals frequency has been changed according to the particular modulating signal or the information signal. The information signal has been lapsed for the highest amplitude level for the longest lapse of time, and it is being reduced its amplitude level and also the lapse of time on the negative side. On the positive side, our information signal has been lapsed for long interval of time and it is having the maximum amplitude. And on the negative side, it is having the lesser amplitude and also the minimum time span it has been occupied. And according to the information signal itself, the carrier signal has been changed its frequency level, not the amplitude level, but it is going to be changing the frequency level. Frequency is nothing but the number of cycles per time, until its ending or where it is going to be changing its positive side to the negative side, its frequency has been increased. That is, if the carrier signal frequency is having 1, 2, 3, 4, 5, 6, 7, 8 cycles or 7 cycles before it is changing its positive to the negative side, it has been increased. That is nothing but carrier signal has having the frequency of 7 cycles per a positive side of a signal. Here it has been changed to more number of cycles before it's changing into the positive to the negative side to represent the maximum amplitude of the information signal and the maximum span of the time. Are you able to understand or not? In the amplitude modulating signal, the carrier has been changed its amplitude, but not the frequency. The carrier has been changed its amplitude levels, right? Here the amplitude levels has been varied. The amplitude levels of the carrier signal has been varied according to the modulating signal. This is the amplitude modulation. But here the frequency has been varied, not the amplitude. Here the amplitude is being uniform. The amplitude is being uniform even after the frequency modulation. But how the amplitude and also the lapse of the time has been indicated is nothing but the frequency levels has been changed. The frequency levels has been changed. See, at starting at the lower level side of the information signal, the frequency has been slightly getting increased. Whenever it reaches the maximum amplitude, the frequency has been completely it has been increased to the maximum rate. And again, whenever it is going to be decreasing to its negative side, its amplitude is going to be decreasing. Again, the frequency is going to be reducing here. This is how the frequency variations has been changed in the frequency modulating signal representing the information signal. This is how the frequency modulated signal will be superimposed on the carrier. Carrier is going to be superimposed. So whenever the receiver receives this FM signal, whenever the receiver receives the FM signal, then he is going to be getting this outlier of the signal according to the frequency levels that he has been received. He is going to be dumping the amplitude levels of the information signal that you have been sent. You have been sent the information signal with these amplitude levels and with this time span. The same amplitude levels and the time span can be decoded in the demodulation procedure of the FM demodulator at your receiver side or receiver device. The particular frequency levels will be detected, and according to the frequency levels that are being detected, the amplitude level of the modulating signal will be get dumped into your FM demodulator device of your mobile or whatever the communication device. This is the frequency modulation, right? Now we'll move to phase modulation. Phase modulation is nothing but the phase angle modulation. That is, the phase angle of the modulation signal is going to be changing. Phase angle of the modulating signal or the message signal is going to be changed. Whenever it's going to be changing its phase, that is positive to the negative and negative to the positive, the representation will be seen, or the representation will be replicated in the carrier signal. See how our message signal is like this. Positive side has been changed here into the negative side, and the negative side of the sinusoidal has been changed to the positive wave, and that is 2 cycles has been given here. One cycle has been changed like this and the other cycle is been like this. Amplitude on the y-axis, time on the x-axis, and the carrier signal is as usual. We taken the carrier signal as with the equal frequency and the equal amplitude. There is no change in it. How this carrier signal is going to be changing or it is representing when our signal is going to be changing its phase. How it is changing its phase, where it is going to be changing. Here it's changing its phase from 30 degrees to the 90 degrees, and again 90 degrees to the 30 degrees, and here it is reaching 180 degrees. It is reaching the 180 degrees. That is, it is going to changing its signal from positive to the negative side, and from the 180 degrees again it is moving to the 30 degrees, and it is reaching again 90 degrees here, and it is going to be changing to the 180 degrees. To complete a cycle, it is going to be passing through 290 degrees and 180 degrees and 430 degrees. And how this particular changing of the phase of our message signal has been represented to the uniform frequency and also the amplitude carrier signal, we see through this phase modulated signal. A 30 degrees change, 90 degrees change, and again the corresponding phase change. 30 degrees and again 90 degrees and again 30 degrees, 90 degrees, and now comes the 180 degrees. Now comes the 180 degrees change. That is, it is been completely shifted its value. That is from positive to the negative. Here, the 30 degrees and the 90 degrees. That 90 degrees is nothing but the peak value. It's been changed to the position. Again, the corresponding 180 degrees, where it has been changed it value, phase angle, right from the 90 degrees to the 180 degrees, it has been moved to the negative side. Whatever may be the phase changes, that is 30 degrees, 90 degrees, and 30 degrees of the negative side has been shown here. 30 degrees, 90 degrees, and again 30 degrees, and also the 90 degrees again. Whatever may be the changes of the signal on the negative side of the sinusoidal has been shown in the negative side of the signal itself on the second phase, on the next phase. And again, a second cycle has been started here. The first cycle has been shown here and the second signal now. This is how the phase change or phase angle change of the modulating signal, phase angle change of the modulating signal has been represented using the same amplitude and the same frequency of the carrier signal. Same amplitude and the same frequency of the carrier signal. So this is how the message signal has been modulated over the phase angles. This is nothing but the phase modulated signal. And if you want to see these three modulations in the single picture itself, this is three modulations on the single picture, that is in a single depiction, how we can see that three modulations are. See, I think you are able to see the screen, isn't it? Are you
Yes,
able to see the modulation techniques?
yes, ma'am.
Okay.
Yes, ma'am.
So this is how the amplitude modulated will be taken. The amplitude has been taken in reference. How the amplitude will be get modulated with the carrier signal and the frequency carrier. According to the modulation signal, the frequency will be varied. Here, the modulation level has been varied. The modulation level is here. The first signal, that is the first one is the modulating signal is having certain modulation. According to the carrier and according to the modulating signal, the carrier will be varied. If the modulation signal is higher amplitude, then the carrier is going to be increasing its modulation level. The modulation amplitude, the amplitude is here at the level of the carrier. But according to the modulating signal, it has been increased, it's modulated, but not the frequency. Not the frequency has been changed, but the amplitude level has been changed. Here, the frequency is normal in all the three cases, either in the amplitude case, frequency case, or the phase case. All the carrier signals are having the same frequency and the same modulation level. But according to the modulating signal frequency, amplitude, or the phase, the carrier is going to be changed. All the signals are the carrier signals itself. According to the modulating signal, if the modulating signal is having the higher amplitude, the amplitude is being raised here. This is called as the amplitude modulation. If the frequency is going to be varied of the modulating signal, the carrier signal is changing its frequency here. The frequency of the carrier signal is original and it is being changed according to the modulating signal. So it is called as frequency modulation. And the phase of the signal is original carrier's frequency phases are like this. Whereas if the modulating signal is having the phases like this, that is, it is not going to be changing its phase until some changes or until some hops, then it is not going to be representing. That is, it is going on positive side itself. The modulating signal is going on positive side. So accordingly, the carrier is also changing its positions. That it's changing its phases on the positive side itself. This is how simply and shortly we can represent what is the amplitude modulation, what is the frequency modulation, and what is the phase modulation. Now we'll go internally and technically how this modulation is going to be represented mathematically, right? second. So what you are going to see here is the carrier frequency is having certain frequency and the amplitude, and the modulation frequency is having lesser amplitude. Even though it is going to be having the lesser amplitude, how the amplitude levels of the modulating frequency will be dumped onto the amplitude modulated frequency signal. A maximum amplitude will be taken and FC plus FM and FC minus FM. 1 second. Here it is not clear. I am going to give you like this. Carrier is having some amplitude, right? That is SM or say FM. Or FC, carrier signal, right? And our modulation signal is having some amplitude representing FM. Then the amplitude modulation signal is going to representing whatever may be the modulation levels. For example, our signal is like this. So it is having amplitude at this level at a particular value, and it is having its level of amplitude at this level, and at this level it is going to be varying in some way. This is the peak amplitude, right? This is the peak amplitude, whatever SM or S0 you are going to represent in the equation. And it is going to be varying from the 0 to S0 and S0 to 0 again, right? How these particular values from 0 to S0 and S0 to 0 will be represented in the carrier, because will be like this. FC minus FM and FC here and FC plus FM. That is how the variation of the signals will be taken, or the modulation levels will be get varied is nothing but amplitude will be taken from FC minus FM value. That is whatever may be the highest peak value will be get subtracted to the 0 level here, and again it is going to be from frequency level, that is the highest modulation frequency levels, to the lowest modulation level values or the amplitude values. This is what that we have represented here, FC minus FM, FC, FC plus FM. That is how the modulation levels, has been represented in different levels of the phase modulator, amplitude modulation. Right? Right. Next one is the frequency modulation. Frequency is going to be varying from point to point. Frequency is going to be varying from point to point. So here, multiple levels of the frequency levels, other than the amplitude modulation, different levels of the frequency will be taken.
Screen is not visible.
Not visible or not clear?
Not visible,
Not visible,
ma'am.
ma'am.
Okay.
Not visible, ma'am.
Yeah, I'm coming. Is it now? Are you able to see now? Frequency modulation. Are you seeing the frequency modulation screen or not?
Yes, ma'am.
Okay. Now you are seeing the frequency modulation now. Other than the amplitude modulation, the frequency modulation will have the number of terms to be varied. Why? Because frequency is going to be varying, its amplitude levels are going to be changing, and the amplitude levels are going to be represented with the frequency levels itself. So that frequency is going to be represented, that is frequency levels will be represented with different levels. Only the amplitude modulation is having only FC, FC minus FM, FC plus FM. That is only. Amplitude is going to be represented in different variations. Here, The amplitude is going to be represented with the variation of the frequencies. So that's why the frequency modulated signal is going to be represented with different levels. How the amplitude is going to be represented is FC, FC minus FM, FC plus FM, and also will reach into the zeroth levels, that is FC minus 5 FM, FC minus 4 FM, FC minus 5 FM or 3 FM, 2 FM. All these levels will also be considered. That is, as the frequency is going to be varying, the frequency is going to be representing your amplitude levels of the modulating signal. Multiple frequency levels are going to be represented and it will be considered into your thing. Okay. And next one is digital modulation. Before getting into the phase modulation, already discussed about the amplitude modulation and also the frequency modulation. And before getting into the phase modulation, we will see what is the digital modulation. What is the digital modulation? So not going with the analog signals. So not only every time going with the analog signals, we are also having the digitized media, digitized transmission and digital transmission of the data itself. How this particular digital modulation will be done? Simply not sending the frequencies and amplitudes over the analog signals, simply not sending the amplitudes and the frequencies over the analog signal and the values of it. We can also send in a binary form or in a digital form. Digital is nothing but again the binary form representing the zeros and ones. How this particular digital modulation will be done? How the data will be sent over the transmission media or the radiation through the ones and zeros. So whenever the signal has been changing or it is going to be converting our parameters into the terms of zeros and ones, then that particular modulation will be called as digital modulation. Until now, we've been considered only the amplitude modulation, frequency modulation, and also the phase modulation. All are represented in the analog signals itself. All the analog parameters we've been taken into consideration, FC, FM, S0, pi, phase, angle, all those things have been represented in the analog parameters. And all those parameters, if they can be represented and they can be sent over the air through the form of a binary values, that is in the form of zeros and ones, then that particular modulation is called as the digital modulation. See here you can see what is the digital modulation? A technique by which amplitude, frequency or phase angle parameters of a carrier or a subcarrier frequencies according to the variation of a modulating signal bit 1 or 0, a modulating bit pair of 0, 0, 0, 1 or a set of 3 or 4 or more bits. That is how you are representing your modulating signal or a message signal, what you are sending from source to the destination in terms of ones and zeros or a combination of two bits, that is 0, 0, 0, 1, 1, 0 or 1, 1, or more than 2 bits, that is 3 or 4. Whatever may be the bits, number of bits that you are going to use to represent your modulating signal, if those bits are in the form of zeros and ones or your value of our modulating signal has been represented in the binary form, taking zeros and ones in consideration, either representing only with 0 and 1 or with the combination of two binary bits or with the combination of more than 2 bits or 3 or 4 bits, then that particular modulation is called as the digital modulation. What you are representing the signal with ones and zeros, you are representing again those three parameters, that is amplitude, frequency or the phase signal. Again, you are representing the three parameters, amplitude, frequency or the phase signal, phase angle. All those will be represented again according to the modulating signal, frequency, amplitude or the phase value, phase angle with ones and zeros. That is different from the analog values. Analog signals are being represented with the analog parameters, whereas the corresponding digital signals or the digital modulating values are represented with ones and zeros. That is difference between the digital modulation and the analog modulation. Analog modulation, what you discussed about previously. Previously, we discussed about the analog modulation of frequency, analog modulation of the amplitude. So before getting into the phase modulation, why? Because this phase modulation is perfectly implemented in the digital modulation. That is before going into the phase modulation. That's why we are discussing about the digital modulation. So whenever you are representing our parameters of the signal using either ones and zeros, that is using the binary bits, then that particular modulation is called as digital modulation. Here also again, according to the parameter that we have chosen, represented with ones and zeros, again we are having the digital modulation in terms of three categories, that is amplitude shift keying. If the amplitude is being varied of the carrier frequency in terms of ones and zeros, then it is called as amplitude shift keying. Otherwise, if you are representing the carrier signal, the frequency of your modulating signal with ones and zeros, then it is called as frequency shift keying. If our modulating signal is a digital signal and its parameters are being represented using ones and zeros, and those parameters are used to refer with the carrier signal that we want to use in the modulation, using those ones and zeros represented by our modulating signal, then our digital modulation signal will be sent over. What our digital modulation signal represent, whether our digital modulation signal is amplitude shifted or frequency shifted. That is, if our modulating signal has been represented using the amplitude of it in terms of ones and zeros, which has been referred with our carrier signal, then we are calling that digital modulation as amplitude shift keying modulation. Our modulating signal has been done with amplitude shift keying and sent over the carrier. Otherwise, if our modulating signal frequency has been represented or superimposed on our carrier with means of ones and zeros, then our modulating signal has been said that it has undergone with frequency shift keying in terms of ones and zeros. Instead of analog representation, here we are doing the digital representation using binary bits ones and zeros. Okay. In the similar way, whenever we are being transmitting zero, this will be represented ASK, that is amplitude shift keying. Whenever you are representing zero, nothing will be represented. That is lowest level of the amplitude will be sent. And whenever you are transmitting one, the peak amplitude of the signal will be sent. That is nothing but how the amplitude variations will be sent. That is the lowest value of the amplitude and highest value of the amplitude. That is, whether you are using ones and zeros, one will be represented with the highest amplitude and zero will be represented with the lowest amplitude. That is nothing but the variation between the analog and the digital modulation, right? And frequency. In the similar way, Fc minus Fs will be represented with 0, Fc plus Fs will be represented with 1. We can change our convention. Fc minus Fs can also be represented with 1, Fc plus Fs can also be represented with 0. According to the number of frequency levels that we want to send, we can change the variations, either 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, whatever the number of bits that we want to represent. Only two levels of the frequencies that we want to send using ones and zeros, then Fc minus Fs will be represented with 0 or 1, or Fc plus Fs will be represented with 0 or 1. Only two values that you are going to use here for representing either the frequency levels or representing using the amplitude levels. Right. And coming to the phase modulation using ones and zeros. So you can also represent in the analog way, but as this particular phase modulation, especially used in this digital modulation, and this is going to be implemented for our advanced digital modulation techniques and advanced digital accessing techniques, we are going to be exclusively discussing about here. That is phase modulation of ones and zeros. This particular phase modulation, especially called as, other than this frequency and amplitude modulation, this phase modulation is being specially called as binary phase shifted key. Even though the same binary representation has been given. Hello, somebody is getting noise at their background. Please mute yourself. Even though the same 1 and 0 is going to be represented in the amplitude digital modulation, amplitude shift keying, and also the frequency shift keying, here the phase modulation has been exclusively used for the digital modulation. That's why this phase modulation is going to be, or phase shifted keying is being called as BPSK, that is binary phase shifted key. That is, the 0 degrees has been represented with 1 or 0, and 180 degrees has been represented with either 1 or 0. According to the angle that has been varied, here you are going to be using that particular representation of 1 and 0. For 0, that is starting 180 degrees, and again it is going to be again molding. That is, signal is being changing over like this. The signal is been changing from 0 and it is been landing over at 180 degrees. That is what we have seen. From right from the 0, it has been landing over to 180 and again 180 to the 0 now. Okay, the total 360 degrees of the signal has been changing from 0 to 180 and 180 to 0. Completely 360 degrees of cycle has been completed. In that, 0 and 180 degrees are represented with 1s and 0. That is one phase of the signal. One phase of the signal will be represented with two values, either 1 or 0. 0 degrees at 0 level, 180 degrees at 1 again. And again from 0 to 180 degrees on the negative side, 1 with 0. That is binary phase shift keying. On a one side, a binary phase will be given, and another side, another binary phase will be given. So exclusively this particular phase shift keying will be used exclusively in the digital modulation. That's why it has been named, even though it is being phase shift keying, it can be also called as binary phase shifted keying. And again you are having here, that is Gaussian minimum phase shifted keying. Gaussian minimum phase shifted keying. Here you are going to use, or you are going to represent minus 180 also. That is not only between 0 to 180 on a one side, we are also having the negative minus 180. That particular minus negative 180 can also be represented using this GMSK, that is Gaussian minimum phase shift keying. Even though if you are having only the positive shift keying or the positive phase angle or the negative phase angle, that can be represented using the Gaussian minimum phase shift keying. See, carrier frequency is like this, and the modulating frequency is like this. 0 is represented with this, and 1 is represented with this. And BPSK is having represented, when transmitting 0, it is having the highest amplitude. And when transmitting 0, it is having the lowest amplitude. That is, you are shifting the phase. You are shifting the phase. Even the signal is having the representation of 0 and 1 like this. 0 is having the minimum value, and 1 is having the highest value. But you are shifting the phase, you are changing the reverse of it. So that whenever BPSK is going to be changing its output, the 0 is going to having the highest value and 1 is going to having the lowest value. 1 is going to having the lowest value. This is nothing but the phase shift. Phase is going to be shifting, right? This is the BPSK. And this particular phase modulation can also be represented with 2 values or either the 4 values. If you are having only the 2 digits, 1 and 0, then it is called as binary phase shift keying. If you are having only the 2 representation, 1 and 0, then it is called as binary phase shift keying. But if you are going to have, multiple combinations, that is multiple levels of the modulating signal values has to be represented. Multiple amplitude levels of the modulating signal has to be represented. Its other degrees can also be shown. Its other degrees can also be shown by having the combination of 1 0, 0 0, 0 1 and 1 1. These 4 are going to be representing other 4 degrees of the wave, other 4 degrees of the signal. Then that particular phase shift keying is called as the quadrature. As you are going to have the 4 combinations, as you are going to have the 4 combination of the phases, then this particular phase shift keying is called as the quadrature phase shifted keying. You are having the 4 combinations, that you are calling it as quadrature phase shift keying. And what these 4 angles represent you, that is 3 pi by 4 minus 3 pi by 4 minus pi by 4 plus pi by 4. 180 by 4 plus 180 by 4 minus 180 by 4 and 3 into 180 by 4 minus 3 into 180 by 4. What are those degrees are? 135 degrees, 225 degrees, 315 degrees and 45 degrees, representing 10, 00, 01 and 11. Right? So as signal is varying, if you are going to representing only the 0 amplitude and the peak amplitude, only 1 and 0 are sufficient for us. But if you are going to show other amplitude levels of the signal also in terms of the phase angle, then you can choose the 4-bit representation which is called as quadrature phase shifted keying, where we can represent the amplitude of the signal at different phase angles, that is at an angle of 3 by 4, at angle of minus 3 pi by 4, and minus pi by 4, and pi by 4. These four angles of the phase angles of the signal can represent your amplitude of the signal or levels of the modulating signal at four levels using the four phase angles. That's why this phase shift keying is called as the quadrature phase shift keying. And this particular phase shift keying can also be implemented to 8 phase shift keying, 12 phase shift keying, 16, 32 are also been available. That is how many number of levels of phase angles can also be shown for your single modulating signal. All those can be represented. That many number of bits representation can also be taken. Okay. And here it is the phase modulation of the BPSK. So the modulating bits are been like this: 111, 4 zeros and 1. The same representation has been given in the QPSK like this: 45 degrees, that is the highest peak amplitude at the lowest degree values, and lowest peak amplitude has been with the highest degree values. That is phase shifting has been done, so that four levels of the amplitude of the modulating signal has been represented using 4 degrees. Four levels of the modulating signal has been represented using 4 degrees of the phases. I think I am clear now, right? How the phase shift keying or the phase modulation will be done, right? So this is about the modulations of frequency, amplitude, and the phases. So after you have been entered into the digital modulation, how the accessing of multiple channels, multiple spectrums, multiple frequencies available in the single band of spectrum, we will see through in the accesses. This is about the modulation, whereas accessing of the multiple bands in the single frequency band of spectrum, we will see through the accessing procedures. Okay, and we'll discuss them in the next class. And this is about the modulation. Here ends the modulation turn, right? Please go through these three modulation, understand how the number of levels of the signal values in the phases, in the frequencies, in the amplitudes will be embedded in a single value or a single wave. How the different levels of the signal in terms of phase angle, in terms of frequency, in terms of amplitude voltage will be taken, so that we'll have an idea that how those will be accessed in your 2G, 3G, 4G versions. How much number of frequency band spectrum can be accommodated in a single frequency band. What you are been talking and what you are been using your frequency spectrums for your networks, that is mobile networks, whether it may be Airtel or maybe Reliance or maybe Idea or Hutch or whatever, Vodafone, whatever it is. We are going to using multiple number of users and multiple number of frequency spectrum. How you are being accommodating, what you are using, whether you're using the frequency modulation, whether you are using the amplitude modulation or maybe the phase modulation. How you are using this, how you are being using these techniques to accommodate those type of frequency bands and the network service providers signals. Right, go through this so you can have the clarity among them, and you will go for the accessing techniques in the next class. Okay, time is over. I'm ending here already. Almost I've taken out of time. I'm leaving here. Get ready for the next one.